is the end of January. In fact, given that it's past midnight, I think it's actually February. But welcome back to all of my viewers to 2019. Nihongo ga daigaku ni benkyou shimashita. Demo muzukashi desu yo. Okinawa ni karate o shimashita. Okinawa no hitobito wa todemo reigi terashi desu. Soshite Okinawa no karate wa kawaii desu ne. But I'm back in Melbourne, Australia. And I thought that for today's video I would read to you a chapter from an old book that I really treasured and as a result have kept for a long time now. I think I found this book in an op shop. I would have been maybe about 9 or 10 when I found this, because I remember I was in primary school. But something that many of you may or may not know about me is that I'm a bit of a nerd, and this book is an old hardback book printed, I think, in the 80s. And it's called The Science in Science Fiction by Peter Nichols. This thing is really interesting, at least to me. It discusses, well, it has 12 chapters in which it looks at many of the tropes and common themes in sci-fi, and it attempts, now remember back then, 1982, it attempts to use their understanding of science back then, which is nearly 40 years ago, and they try and talk about some of the possibilities or the misconceptions of science fiction, where they get things right and where they get things wrong, or where one thing may be possible via one method but not possible via another. There are 12 chapters. The first one is Journey into Space, which is all about space travel. The second is The Secret is Energy, which is all about ways of producing energy, whether that's hydro or wind power or solar. Chapter 3, Aliens. Chapter 4, The Limits of the Possible. So that sort of goes into things like faster than light travel, hyperspace, instant communication, things that at the time, 40 years ago, were thought of as distinctly far away. Chapter 5, Time Travel and Other Universes. Chapter 6, Holocaust and Catastrophe. So that's sort of about end of the world scenarios and warfare. Chapter 7, Intelligent Machines. So this covers AI and robots. Chapter 8, Men and Supermen. So, in effect, that effectively explores transhumanism and posthumanism. Chapter 9, Dreams and Nightmares of the Future. So a lot of that is about technology that may make our life better or hellish. Chapter 10, Powers of the Mind. Now, a lot of 80s sci-fi often involve things like ESP or telekinesis or psychokinesis. Yeah. Chapter 11, Mysteries of the Past and Present. So that kind of goes into the ancient astronaut theory. And then finally, Chapter 12, Where Science Fiction Gets It Wrong. And so this elaborates on everything that is just, according to their understanding of physics back then, is completely impossible. So, what I thought I would do, because I am a massive nerd and I find this stuff very interesting, is that I would read to you guys the first chapter about star travel. I remember when I was about 8 years old. I mean, okay, get ready, story time. Well, ever since I was young, I was brought up on a fairly steady diet of hero movies. And unfortunately, a lot of these movies were too violent for me to watch, so I would have to watch Disney and other sort of childhood movies. But one of the exceptions to this was Star Wars. I loved Star Wars. I was able to watch it, I think, since the age of about 4, before I could even understand what was happening. And to me back then, it was very much a common point between me and my cousins that I grew up with. We would watch the old VCRs and rewind them and skip through all the boring interviews and special effects documentaries and things. And we'd get to the meat and bones of it, which was really just us trying to find everything where there were lightsabers and battles and spaceships. You'll have to excuse the noise in the background. Dax, my dog, has a cone on her head and she's very upset. So, growing up, I was always very much into my science fiction. And when I found this book, I found it incredibly interesting because it dissected some of the things that I love about science fiction. So, let's move on. Chapter 1, and we'll read it one page at a time. Now, this book has a lot of diagrams, but as you can see, it's a little difficult for me to find the focus point with my lighting, so I would say that the best way to enjoy this video would simply be to sit back, relax, maybe with some headphones, and just enjoy the trivia. Chapter 1, Journey into Space. And let me quickly remind you again that this book was written in 1982. Dax is getting comfortable. Man has landed on the moon, and unmanned probes have visited Mercury, Venus, Mars, Jupiter, and Saturn. But how likely is it that mankind will ever reach the stars? This, for many years, has been the dominant theme of science fiction. man has done well in his conquering of the solar system. In half of a century, we have progressed from flimsy biplanes to the landing of man on the moon. We are still a long way from landing man on the other planets, but we have taken the first steps. Space probes have landed on Mars and Venus and have photographed Mercury, Jupiter, and Saturn at close range. But visiting the stars means travel on an almost unimaginable scale. Today, Apollo craft take 3 days to reach the moon, approximately 375,000 kilometers away. In 1973, it took Pioneer 10 21 months, achieving a speed of 14 kilometers per second to reach Jupiter. It will leave the solar system in 1987, and if it were pointed at one of the nearest stars, Alpha Centauri, which it isn't, it would take over 80,000 years to arrive, and there may be little point in visiting Alpha Centauri. For a long time, it was thought that the nearest star with any likelihood of possessing a planetary system for possible colonization was Barnard's star, which is nearly half as far again as Alpha Centauri. But very recent work has cast doubt even on this. We have now aimed 4 probes out of the solar system, Pioneer 10 and 11, and Voyager 1 and 2. But it may be 1,000,000 years before any of them passes close to a star, although they bear messages for any alien race they may encounter. We usually measure interstellar distances in light years, the distance traveled by light. That is 300,000 kilometers per second in 1 year. It takes light from the sun about 8 minutes to reach us, and 5.5 hours to reach the outermost planet of our solar system, Pluto, which isn't a planet anymore. It takes 4.3 years for our sun's light to reach Alpha Centauri. So far, we have talked only about the closest star. Our galaxy alone contains around 100 billion stars, and it is 100,000 light years across. There are only 2 strategies for overcoming the problem of distance. Our starship must either go very fast or support its crew for a very long time. The slow strategy is perhaps the easier, though less attractive, since only our remote descendants will ever know if we were successful. There are 2 ways of carrying out the slow strategy. One is to launch a generation starship in which the crew completing the mission consists of the many times great-grandchildren of the crew that set out. The other is to put the crew members into suspended animation. If they could sleep for thousands of years, the slow strategy would be more feasible. What about the other strategy? How do we make a starship go very fast? It is possible, but there are practical problems. The ideal propulsion method would give the Starship a continuous acceleration equal to the force of Earth's gravity. This would quickly build up velocity, as well as giving a comfortable ride for the passengers. But is it possible? We know two ways, basically, of propelling a starship. Either we push it, as by using the pressure of a laser beam, or it pushes itself. Our present-day rockets push themselves by ejecting mass at high speed. Newton's third law of motion, that every action has an equal and opposite reaction, operates here. As the mass, the propellant, is pushed backwards, the rocket is accelerated forwards. There are only two factors that can be varied: the mass of the propellant and the velocity of ejection. The easiest way, of course, is to use a lot of mass, but this is the method with the greatest practical problems. Although our present-day moon rockets use exactly this technique. The trouble is that the heavier the rocket, the more propellant is needed to push it. Liquid chemical propellant is itself heavy. Thus, most of the propellant of our modern moon rockets is in effect wasted by being used to push the mass of the propellant, which will be used later. One analogy would be to think of a moon rocket as being a car consisting of 99% fuel tank and 1% room for the driver. Most of the fuel would be used up in driving the fuel tank along. The problem is made easier by using multi-stage rockets. One of my resolutions for 2019 is actually to build a multi-stage amateur rocket. Stay tuned. As the propellant in each stage is used, the heavy casing is dropped off. But this is only a partial solution. Human passengers can only withstand so much acceleration. A very fit man can withstand the pressure of an acceleration equal to around 15 times the force of Earth's gravity for only a few moments. Our present moon rockets accelerate powerfully for a few minutes and then coast the rest of the way at a constant velocity, with the occupants feeling the discomfort of weightlessness or free fall. Initially, free fall often leads to nausea. Then, for a while, it's fun. After periods of a week or more, it leads to muscular weakness and a leaching of calcium from the astronauts' bones. It is generally agreed that a superior method of rocket propulsion, especially once the ship has left Earth's gravity well, would be a long, slow acceleration. Starships of the future will probably not leave from Earth. They will be constructed in space. If they used a method of propulsion giving an acceleration exactly equal to the force of Earth's gravity, and if this acceleration was continuous, to the occupants of the ship it would be indistinguishable from true gravity. The back of the ship would seem to be down, and there would be none of the physical inconveniences associated with freefall. Other forms of imitation gravity are quite possible. The simplest is to have a starship shaped like a wheel which spins. The centrifugal, force would feel like gravity, and the edge of the wheel would appear to be down. With this system, the closer to the center of the wheel, the lower the gravity. At the hub, there could be a free-fall sports center. The velocity of a starship undergoing a continuous acceleration of 1g, that is 1 Earth gravity, would mount up surprisingly swiftly. The ship would travel half a light year in just under a year of continuous acceleration. But how could this be achieved? Could any ship carry the propellant for such continuous acceleration? But what about slowing down at the end of the trip? There is no perfect answer yet, but man's ingenuity has, at least on paper, carried him part of the way. A rocket which has used a nuclear fission reactor as a drive would achieve a much higher velocity than one using our present-day liquid or solid chemical propellant, since the power would be so much greater than that given by ordinary combustion. But even the most efficient of nuclear engines, oh my goodness. I'm making a lot of mistakes here because it's about 2 or 3 a.m. But even the most efficient of nuclear engines, and with shielding that would be rather heavy, is unlikely to give more than 10 times the efficiency of a chemical rocket. Such an engine could plausibly accelerate a starship to 1,125 kilometers per second before running out of propellant. But even then, it would take around 1,000 years to reach the nearest star. The British Interplanetary Society has come up with a carefully designed variant of the atomic drive called Project Daedalus. It consists of an unmanned rocket in 2 stages, designed to fly past Barnard's star and send back information. The trip there taking around 50 years. After accelerating to 13% of the speed of light in about 4 years, the spaceship would coast the rest of the way. Project Daedalus relies heavily on technologies not yet available to us, but the basic principle is generally regarded as sound. Small pellets of thermonuclear propellant are projected into the reaction chamber and bombarded by high-powered electron beams. Nuclear fusion, not fission, results, and the exploding plasma, unimaginably hot and energetic, is swept out of the ship. The electron beams are powered by energy removed from the hot plasma by an induction coil as it leaves the ships. In other words, the drive consists of a series of very small pulsed H-bomb explosions at the rate of 250 per second. The particular propellant chosen results in reaction products which are all charged particles. The designers did not want any neutrons resulting from the explosion because, as the neutrons are not charged, they cannot be channeled by magnetic fields, and heavy shielding would be required. So, as a side note, all of this is happening at a subatomic level. Like, I actually wasn't aware that back in the 80s they had this kind of idea. But anyway, unfortunately, helium-3, which is one of the fuels that they were talking about, is extremely rare. The designers believe we should need to extract it from the atmosphere of the planet Jupiter, where it is much more common. This is not a project for the near future. But now we have Elon Musk, so some scientists believe that a much more workable system of propulsion would be the ion drive, or electric drive as it is sometimes known. Such drives on a small scale have already been used for orbital adjustments to satellites. An ion is a charged particle, such as an electron or a proton. It carries an electric charge and can therefore be bent in its course or accelerated by a magnetic field. Any atom can be ionized by stripping it of electrons, which carry a negative charge, leaving it positively charged. The heavier the atom used in the ion drive propellant, the greater the thrust. Mercury is a conveniently heavy but not very expensive element, readily ionized, and is the likeliest propellant. Considerable power will be needed to create the massive magnetic fields required to accelerate these ions to very high speeds. This power could be obtained on a small scale by solar batteries, but on a larger scale, a nuclear fission plant would probably be needed. Dr. Leonard Jaffe of Jet Propulsion Laboratories in California believes that the nuclear ion drive combination represents a more workable propulsion system than Project Daedalus, one that might be completed by the year 2000. I'm not sure if I'm saying this right, by the way, Daedalus and the conventional ion drive have an important factor in common. In both cases, the amount of mass per second ejected from the ship is quite small. The work is achieved by the immense velocities of ejection. The acceleration would also be small, well below 1g, because of the tiny masses involved. But because the rate of ejection is low, the propellant can be conserved for a long time, and the acceleration can be continued for years if necessary. Project Daedalus would achieve greater velocities than the conventional ion drive, but presents far larger technical difficulties. Both, however, are realistic schemes in terms of present-day technology. If technology advances at its present rate of progress, then this sort of engineering should be quite possible in the 21st century. I think we just invented iPhones instead. It can be seen that most Starship schemes try to evade the difficult requirement of carrying a lot of heavy propellant by using high velocities of ejection. But perhaps there is another way of meeting the problem. Is it necessary to carry fuel at all? Dr. Robert L. Forward of Hughes Research Labs in California has proposed using the pressure of light itself as a propulsion device. An array of laser beams would be built in space close to the sun, forming a circle of 250 kilometers in diameter. They need not be remarkably powerful. Dr. Forward suggests the figure of 35 megawatts. The lasers would be beamed in unison at the Starship, which would carry a huge, thin, rigid sail of metal. The pressure of the lasers on the sail would accelerate the ship up to velocities where relativistic effects would begin to become perceptible. Slowing the ship down at the other end would be technically complex. I think by relativistic effects they mean Einstein's theory of traveling at such a speed that time would seem to be distorted for the people on board. I think that's what it's saying. Anyway, briefly, the ship would swing around the target star and be decelerated by the same lasers on the way back. The difficulties of building a working starship are great. One problem is that kinetic energy increases according to the square of velocity. So, to get 10 times the speed, 100 times the work is required. Another is that according to Einstein, the mass of the ship itself increases as it approaches the speed of light, and thus a correspondingly greater amount of propellant would be needed. But there may even be a way around this. They're referring to a ram scoop engine, which is mentioned later in the chapter. There is a simple, cheering final point about starships. For most purposes, space is a vacuum. Conventional streamlining is not needed because there is no air resistance, so a starship can be literally any shape. A cluster of spheres, a delicate nautilus-like spiral, or a tiny cockle shell carrying a great silver sail many kilometers wide. Engineering and aesthetics can finally marry, the consummation no longer prevented by such earthbound difficulties as gravity and friction. Starships could be unutterably beautiful. There have already been inspired designs by science fiction illustrators, and there is no reason why the great ironclad space hulks of Star Wars and the black hole should not give way, both in films and in reality, to starships of a fragile and airy filigree like snowdrops or feathers or thistledown. So right now, we have the two choices: a generational starship or cryo-sleep type of starship that travels slowly, or a fast one. And they've spoken about the ion drive versus nuclear energy. The ion drive requires extra fuel after it's arrived at the ship, at the star. The ram scoop engine idea is now what they go into. So I think we'll finish this off with the ram scoop engine idea. One of the most popular kinds of starship in science fiction is the Bussard ram scoop. The design for this spacecraft was suggested by the American physicist Robert Bussard in 1960. The beauty of Bussard's system is that it avoids the problem of carrying massive amounts of fuel by undertaking continuous refueling while in space. Space, even that between the stars, is not completely empty. By far, the most common element in space is hydrogen, which is the basis of most nuclear fusion reactions. If a spacecraft could somehow collect enough hydrogen from space as it traveled, this could be used to fuel a fusion drive. But by earthly standards, interstellar space is close to an absolute vacuum. There are only 1 or 2 atoms of hydrogen per cubic centimeter in interstellar space. A gas density only 10 to the power of negative 24 of that at the Earth's surface. This is not much, but consider what would happen if, using a conventional ion drive, we accelerated a spaceship to around 1% of the speed of light. At this velocity, the spacecraft would be traveling so enormously fast through such a huge volume of space every second that the almost vacuum through which it traveled would appear to be relatively dense with hydrogen, in the same way that a plane meets greater air resistance the faster it goes. At this velocity, it is believed that the spaceship would meet with enough hydrogen to begin collecting it as fuel. Even then, however, the hydrogen would still be so tenuous that the hydrogen scoop would need to be gigantic. The invisible, funnel-shaped scoop would consist of a vast electromagnetic field projected from great superconducting coils. This would ionize the hydrogen atoms and magnetically funnel them back into the fusion engine. Even a comparatively small starship weighing 100,000 tons would need a collecting field, a scoop with a radius across the funnel of 34,100 kilometers. That's from the center to the edge, not the whole way across, which is more than 5 times the radius of Earth.